Okay, if you're watching some of these chapter 10 videos back to back, the organ music should be done. Again, I apologize for that. Hopefully we can use those videos since they aren't too long. All right, so goals here for this one are two. Very briefly, some comments about anaerobic environments. So this is section 10.8. And then also I have something that I think is somewhat in the book, but then I added some things to it, which I'll get to. So just doing a few notes here, and then kind of a big diagram. So I'm gonna erase the board once during this. So this is letter D, and section 10.8 primarily. Yeah, so anaerobic considerations, and again, the notes you have there are fine. This is not all that common. Aerobic considerations. So where do we get an anaerobic aqueous environment? A bunch of them are listed here. So, and since I'm not doing this as a lecture with these slides, I'm not showing these things one by one. So stagnant water, swamps, deep lakes. There's a video that I put there. Hopefully that link still works if you look at the slide. So if you live somewhere where there actually are swamps, I actually don't know where the closest swamp is to where I am. Probably down in Virginia somewhere. I'm assuming there's some swamps down there, but I don't really know. Landfills are definitely something that we have around here. In fact, there's a landfill in Franklin County, I believe, which is just south of Cumberland County, that actually collects the methane gas that comes off the landfill and then uses it for, I think, energy production. That's called biogas. Then you also have bacteria, which you can see what those are called, methanogens. I thought that was kind of a fun term. So it's a bacteria that makes methane, okay, kind of like cows, I suppose, or ruminants in their stomachs. And then a couple of definitions there. These are ones I just lifted right from the book, because we're going to come into these a couple times. So disproportionation is just a type of redox where the same thing is oxidized and reduced. I'm going to show an example of that. And fermentation, if you're into ferments like yogurt or fermented vegetables or kombucha, or things that are fermented, typically associated with foods. The definition of fermentation, you can read that there yourself, is it's also redox, where both oxidizing and reducing agents happen to be organic matter. So just some good definitions there. I'm really summarizing this section. There's not a ton to do here. In fact, this is why this one I'm going to combine two things. Is a little bit about anaerobic considerations. Another example of balancing a chemical equation. I don't know, I'm going to look at the book right here. I should look at this ahead of time. The book in section 10.8 gives you the overall redox reaction. I'd like to actually go through that and show the oxidation half reaction, the reduction half reaction, just to get a little bit more practice. Not that we need a ton. And then I'll save what I'm going to do later. Okay, so the book gives you this. So you take, this is the answer, if you will. This is the overall redox equation that's already been worked out for you. It's not particularly complicated. Like, you really don't need to do redox to balance this. So this may be a little excessive for what we need to do here. So you have 2 moles of our generic organic matter, polymerized carbohydrate, and that's simply turning into methane and carbon dioxide. Now this is under anaerobic conditions. So what's actually facilitating this? This is more biology than chemistry. So I'm just going to call this bacteria. So this is not an environmental biology course, not a chemistry course, and we're not going to go through all of this. This is a disproportionation reaction. The same chemical is being oxidized and being reduced. So that is our oxidation half reaction. We are literally adding more oxygens to the carbon. So by default, This is our reduction reaction that's happening. And what we're going to do here is assume we don't have this balance. So we have generic organic matter being reduced and oxidized to methane and carbon dioxide in an anaerobic environment. So, because this is not involving plus oxygen. It's as simple as that. It's an anaerobic environment, so there's no oxygen on this side of the equation. So what I want to show you here is that's literally what it means. No O2. Is to go through the balancing of this one. And that's again a little excessive. So we're going to do our oxidation half reaction, our reduction half reaction, and the overall redox. And we already know the answer. That's the answer. You don't really need to do the redox, but I think it's helpful to do it. So let's see what we got going on here. I have these in reverse order in my notes. That's okay. I think I can handle it. So we've got the oxidation half reaction starts off like this. The reduction reaction, again, disproportionation, same chemical, both being oxidized and reduced. And let's balance it. And let's assume, as we typically do, that we have an acidic environment. So let's see. Do this one first. So got carbons, that works. Hydrogen, we need another oxygen, don't we? So I think we need to put a water here. And then we have to put 4 protons, H plus there. And then plus 4 electrons. I think that works. Yeah, that works. And then here, we have to put oxygen, we have to put a water over here. Hydrogen, we have 2, 6, so 4 H plus, which it better cancel with those because there's nothing left over in the final answer. So we better get the same number of H pluses and electrons, to be quite honest. Yeah, it better be, it is 4 electrons. So this is actually a pretty easy redox one to get your head around, I think. Just instructive. Is it really that useful? Not that useful. But 2CH2O goes to CH4 plus CO2. Now, why are we doing all this? First off, it's good because we just have some anaerobic environments. Methane is a molecule that gets discussed a lot. This is really not that crucial for aquatic chemistry. You don't see a lot of chemical reactions of methane in an aquatic system. You see it in the atmosphere. This is a very potent greenhouse gas. So this typically is not, it's low solubility, so, well, because it's non-polar, okay, so it's not crucial for aquatic chemistry. It's more crucial for atmospheric chemistry. So that's why we don't spend a ton of time talking about this. Okay, before we go on and talk about specific case studies of other molecules like sulfur compounds and things like this, when I taught this course for the first time, I don't know about you, but my brain has a tough time fitting all these pieces of the puzzle together. So what I did in the course, I occasionally would take a step back and try to come up with some kind of graphic that summarizes the takeaway things. And I'm pretty sure I did this, no, I'm not pretty sure. I did this for atmospheric chemistry, like just some big picture takeaway lessons. And I got to the point when I was teaching this section where I wanted to do that for what's going on here. And namely what I have here is a graph that talks about chemical stratification in lakes. And it's really, looking back here, it's not much different than, let's see, where was I inspired by this picture in your book? And by the way, you've already noticed that we're skipping around quite a bit. Like figure 10.3, where you have, it says aerobic conditions, where it's warm water, anaerobic conditions with cold waters, like going down into a stratification in the lake. I just got to the point where I'm like, you know what, I need something a little bit more than this to help me keep track of what's going on. So I'm going to make a graphic here. I don't know if it helps you, maybe it just helps me, but just give me a second, and I'm going to make a diagram that's probably going to take up the main space in one whole page. And if you want to give this diagram a title, well, it's the chemical stratification in the lake. And we're not really going to talk about the temperature inversions that happen in the winter, so it's a perfect time to be talking about this. I'm making these videos in the summer of 2026. So this would be very applicable to any lake, like possibly, like I showed you before. So, give me a second here. So we can't separate the atmosphere from the aquatic system. So I'm going to go top down. And whoa, terrible handwriting. So recall that the first layer of the atmosphere is called the troposphere. So that's about, what is it, 15 kilometers in altitude. These are always good things to remind yourself. And the troposphere has about 85% of the atmosphere by mass. We've done that before. Good reminder. So let's pretend that you have the troposphere and it's coming into contact with a lake. I'll make sure this is pretty big. Not a graphic designer, can you tell? So we have a lake, a deep body of water. Most of the chemistry we've talked about would be like a stream or the surface of a lake, where it's an oxidizing environment that changes as you go down. This is both a summary of things we have done and a preview of coming attractions. So things that we discussed in the previous part one of the course, in the troposphere, we have pollutants like our SOx, our NOx, then we have naturally occurring compounds, which are very important, carbon dioxide. We also have particulate matter. We have carbon monoxide, a pollutant, dihydrogen sulfur. So we have those kinds of things up here. And again, this may be more for me than you. And to understand the atmosphere, what kind of math do we have to do? Well, we have to do PV equals nRT. We have to pay attention to what units we're using. And we have to do a little bit of stoichiometry. So to understand the troposphere, that's a gross simplification. But now, when we come to a lake, so I suppose we should use different colors, but I'm not going to. And you have the surface of the water. You have these gases in equilibrium with their aqueous, aqueous counterparts. Now, how do we get a hold of that with the requisite math? Well, that's where we use Henry's law. So the concentration of that gaseous species is the Henry's law constant times the partial pressure of that component. Oxygen is one example we can do. That's fine. Okay, so when this happens, the top layer, and I forget if this is in the book or if I got this somewhere else. Probably not. I just thought this was pretty interesting stuff. I'm going to divide this into 3 layers, so 3 strata. So this is chemical, so not biological, stratification, layers, in lakes, or really any deep freshwater system. And this is mainly in the summer. Okay, so what's going on here? So I found this useful. So the top layer, is an oxidizing environment. Then you have kind of a middle layer, and then you have a lower layer. Makes sense, logically. Let's chop things up into a 3. These are given names. The top layer is called the epi, I'm gonna look at this one. Limnium. I think people that study lakes, it's called limnology. Is that right? I think. And this would be approximately the same as rivers, streams, etc. Creeks, or if you're from western Pennsylvania, that would be a creek, like me, western Pennsylvania. So the epilimnium is where you have the oxidating environment, so that's aerobic. It's an oxidating environment. These are all synonyms for the same thing. Again, this was useful for me to get my head around. And so here you have a lot of redox chemistry taking place. And some of the things that are really important up here, some chemicals, and trying to, this gets a little sloppy, is nitrates, which we've discussed, are really important here. Sulfates are really important here. Now these are the most oxidized forms of nitrogen and sulfur. There is no NO4, there is no SO5, so that's the end of the line for those things. That's why you talk about them in the epilimnium. Then something we are going to talk about a little bit later in this chapter is iron with a +3 charge. A very important ion, especially in areas where there's a lot of mining and a lot of acidic mine runoff. Not just, it's not a pollutant necessarily, but it's a very important ion to consider. That's the most oxidized form of iron. There's iron +2, there's iron +3, there is no such thing as iron +4. So again, the end of the line when it comes to iron. And that is actually insoluble iron, if you want to write the word insoluble. So iron with a +3 tends to form insoluble solid compounds or insoluble precipitates. A little bit redundant to say insoluble precipitates. It forms precipitates. Another thing we have to consider, which we will in much greater depth, is the following equilibria. Is H2CO3 carbonic acid in equilibrium with bicarbonate in equilibrium with carbonate. That's really a whole lesson unto itself, because this is chemistry that occurs in every natural system because of carbon dioxide gas. So that gets channeled into this system, and depending on the acid base. So some things we need, other things we need to be able to do chemistry-wise in terms of math is acid-base equilibria, so Kas, Kbs, pH, all that. We can't forget our redox chemistry. We have to remember a little bit of Ksp when it comes to precipitates forming, and a little bit of math that I've introduced to you here. Biological oxygen demand, more important for this layer as we go. Okay, some other chemistry I thought was useful for the big picture, so this is where we've been spending a lot of our time. The middle, often, if it's not the top, it's not the bottom, it's the middle, so the synonym or the prefix meta is often used in those cases. This is called the meta-limnium, and this is also given another name called the thermocline, as that word would suggest. This is where you get a rapid decline in temperature. Anybody that's jumped into a deep lake in the summer, you feel this. You jump into the lake, and you, as you sink down into the deep lake, like the Finger Lakes or something like that in New York, or just something that's a deep lake or a reservoir, it gets cold pretty fast, and you got to be very, very careful. If you go down too far, you can get hypothermic pretty quickly if you go down to the thermocline and stay there too long. Typically, you won't, because you'll need to come up for air. And then finally, you have the hypothermic in cellular intelligence, you can parse words just like anybody else, so you're below the limbium, you're in the lower levels of this. So what kinds of chemistry do you have happening down there? Well, you have, if you will, sometimes the opposite chemistry of what's going on. So you have iron plus 2. And this is where you get more soluble iron compounds, so not precipitates, things that will stay dissolved in water. You will get not sulfates, but hydrides of sulfates. Interesting. You won't get carbon dioxide, carbonate, bicarbonate, carbonic acid. You'll get methane. We're talking about an anaerobic environment now. We're not talking about nitrates at this level. We're talking about things like ammonia production and ammonium production. So in hypolimbium, we tend to be anaerobic and a reducing environment. So I just find these sort of pictures helpful in the overall, just to get a perspective on things. So we're not losing perspective, not losing our mind. So that when you see where you are, depends on the chemistry that's happening. It depends on the math that you apply. And that's really all I wanted to do, is take a step back and look at the big picture before we start mining down. Kind of a pun intended, since we do have a lesson on mining. And I'm going to leave it there. And I think the next section we're talking about is sulfur compounds. And again, we're kind of bouncing around this chapter. This chapter could almost be an entire course unto itself. So we're going to keep being selective. So I hope you found that sort of big picture, step back, useful. If not, that's fine. It's probably not going to, maybe you understood that before. Okay, that's where we'll end this one.